The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone, I welcome the viewers of another episode of my video series on the Earth System. In this video, I would like to discuss again some aspects of spreading zones. This time it's about their location in the large plate tectonic framework of the moving plates. That means, where are they located and how does their position change over time? And as with all other videos, I would like to point out the opportunity, giving me feedback if you have any questions or comments. You will find my email address on the first page of this video or on the website. Before I get to the movements at spreading zones, I would first like to explain at least a few geometric relationships that are important for the location of spreading zones on a globe. In a later video, I will go into the geometry of plate movements in more detail. With this video, I'm going to briefly explain the difference between relative and absolute plate motion, and then I want to show that the position of the spreading centers has a lot to do with it. We know that the lithospheric plates move on the asthenosphere. North America, for example, is moving away from Europe by 2 to 2.5 centimeters every year. But which plate is actually moving? If we look at it on a ball, it's not that easy to say. Is America moving west and Europe stays on site? Or is Europe moving east and America stays on site? Or are they both moving in different directions? How does it relate to this framework of plate motion directions? If we want to describe a movement in a mathematical sense, we need a reference. Something moves from point A to point B. Or we say we are standing at a location A and something is moving away from us to point B. This of course applies to plate movements. In order to describe such plate movements, we need a reference point, or let's better say a reference system. When I say that America is moving away from Europe at a rate of just over 2 centimeters per year, I'm referring to the European plate. That means America is moving 2 centimeters westward relative to Europe. My reference system in this case is Europe. And I use it to describe a relative plate movement and the relative speed of the movement. But I could just as easily stand in America and say that Europe is moving 2 centimeters to the east relative to America. That amounts to the same thing. And then the question comes again. Who is moving in which direction? Because we are on a big sphere. Let's have a closer look at this movement, again at a spreading center. Schematically, this figure roughly corresponds to what happens between America and Europe. The 2 centimeters gap that opens between the two plates every year is filled with new oceanic crust. 1 centimeter of it belongs to America, 1 centimeter to Europe. The gap remains in the middle of the spreading zone because the spreading movement is always symmetrically. Just to understand the scale that we are talking about in plate tectonics. With a spreading of 2.5 centimeters per year, in a million years, a 25 kilometer wide strip of new oceanic crust will be formed. That means on each side of the spreading zone, the plates grow by a strip of around 12.5 kilometers width. If we extrapolate that at 2.5 centimeters per year, that's already 2,500 kilometers in 100 million years. And that brings us to the actual dimensions that can be proven today. The oceanic crust between Europe and North America is approximately 2,400 kilometers wide. And if we now assume that the opening of this part of the Atlantic occurred in the Middle Cretaceous, almost 100 million years ago, this corresponds almost exactly to these values. So much for the dimensions. Let's go back to the movements at the spreading zone. We can also achieve the same result that we have just looked at, that is 2 centimeters of spreading, 1 centimeters of new oceanic crust on each side, if we consider one side to be stationary. Here in this figure, we fix the plate on the right side. In this case, the spreading zone shifts and the left plate moves away at twice the speed. The main difference between the two models is that in the first case we consider the spreading zone to be stationary, while in the second case it changes position. And this is particularly important with regard to the mantle flows in the flowable asthenosphere. I will demonstrate that the location of the spreading zones is not fixed. And I will show this using a very prominent example. In order to be able to really determine in which direction a plate is moving on the globe, I need a reference system that is independent of the individual plates. But since all the plates on the Earth's surface move in some direction, not a single plate in the world is suitable for such a reference system. So what can we do? We need something that is independent of plate movements and provides us with fixed points on the Earth's surface. And now the hotspots come into play. These are fixed points because we assume that the hotspots remain in the same place for many millions of years. That means they are stationary in relation to the globe. I will also explain this in detail in a later video. For now, it should be enough that we can use these hotspots as a reference system. We know that the plates move across the hotspots. That's why we can use them to determine the real plate movements on Earth. We then speak of the absolute plate movements as opposed to the relative ones. Generally, based on these considerations, we can now say that spreading centers are not stationary and their location depends on the absolute plate movements. In the vast majority of cases, we are dealing with symmetrical spreading. That means that newly formed stripes of oceanic crust are of equal width on both sides of the spreading center. Using the example of the spreading between South America and Africa, I will show how the plates move away from each other, but they behave differently than you might expect and as it is often shown in some animations on the internet. In this figure you can see the relative plate movements in white, for example the already mentioned 2 centimeters between Europe and North America, or the 3.4 centimeters between South America and Africa. The absolute plate movements can be seen in yellow, which of course always apply to the plate as a whole and not just at the respective plate boundaries as with relative plate movements. You can see that the relative movements in one and the same plate can be quite different. Here, for example, the Indo-Australian plate, which is moving towards Eurasia off Java at 8 centimeters per year, but only at 5 centimeters on the Himalayas. This has to do with the spherical shape of the Earth, and I will also explain this in more detail in another video on the geometry of movements. Africa moves north very slowly, just half a centimeter, while South America moves west with a slightly greater speed of 3.4 centimeters. The spreading velocity in the middle of the Atlantic is about the same, and there is a reason for this, because the African plate can be viewed as more or less stationary, as in my schematic example just shown before. We will see this in a short video clip. This video clip shows a model of the opening of the South Atlantic between Africa and South America. The South Atlantic opened a little over 110 million years ago, and since then the South American plate has been drifting westward, with reference to the hotspot reference system, which I explained just before. What we consider here is the absolute plate motion. The African plate remained almost stationary, drifting just a little north, but definitely not west. And this results in the continuously changing position of the spreading center. In this case, it is also shifting westward, but only half as fast as the westward drift of the South American plate. This is exactly the same principle as what I showed earlier in the model. The spreading is relatively symmetrical, and with respect to the spreading zone, the plates move away from each other at the same speed. If we were to stand on one side of the spreading zone, it doesn't matter which side, we could see that the other side is moving away from us by 2 centimeters. But with respect to the hotspot reference system, only the South American plate is moving while Africa remains roughly stationary and drifts just a little north. How such spreading works and how their position changes again and again can be observed beautifully in a natural model in an active lava lake. I'm showing a time-lapse video that is available on the United States Geological Survey USGS website. I have linked the video on the website so you can watch it independently of this video and in better quality. In this video, taken in 2016 at Kilauea's Halemaumau crater in Hawaii, you can see red fissures opening and pouring out liquid lava. It cools down on both sides and becomes black, which is why you can see it so beautifully. But you can see how the red fissures that we use as a model for the spreading zones move. The hot material comes up at the fissures, like at the mid-oceanic spreading zones, and you can see here very nicely how these gaps shift. They are not stationary, and they move sometimes slower, sometimes faster. And that's just the main thing you can see here, is that they are constantly changing their position. This is exactly how you have to imagine the mid-oceanic spreading zones, based on geological periods of many millions of years. Of course, you can't equate everything that happens here one by one with the plate movements, although something like subduction can also be observed here at the edges. But for the mechanism of the spreading zones and their changing positions, this is an extremely impressive and, for me, quite convincing model. Here is another photo of the same lake. Here in the lava lake, the lava comes up under these red fissures, and the cooling lava, which then of course turns black, drifts away from the fissure. In the bubbling lava lake there are small convection cells under these gaps in which the heat is transported upwards. I have indicated these convection cells in this sketch just to show how we can imagine it. The liquid lava moves under the cooled and then solid lava sheets, and the heat released in the fissures creates convection currents. The current goes downward on the side, as we just saw it in the video, and then it comes back up in different places and drives the individual pieces of lava apart. Of course, they can't remain stationary because lava pours out a crack and flows outwards. It pushes away the cracks next to it. That's why we see such a strong sideways movement of the fissures on the lava lake. Well, that should be enough for the plate movements in spreading zones. In the next video, I will first deal with the Earth's magnetic field and then with the magnetic stripe patterns and spreading zones, which tell us something about the symmetrical formation of new oceanic crust. This time, thank you for listening, and I'll be happy if you stick around. And I recommend continuing with the video on the magnetic field of the Earth.